Hey there. So we're going to talk about special types of ideals here. So we have prime ideals, principal ideals. Let's see, prime ideals, maximal ideals, and principal ideals, I guess, are the three things we're going to look at here. Actually, just prime and maximal for this particular thing. So what is a prime ideal? So remember, for now, right, a prime number, so A. Let's see, and I guess we can do this. We can do this in any ring. So A subset of R is prime if and only if when A divides BC, then A divides B or A divides C. Okay, so that'll be our definition of prime. There's another definition, which is A would be the only thing dividing itself other than 1. We're going to look at that more later because these actually are two different notions. So this is going to be the definition of prime element, right? And I guess nothing's really required here about the ring except that it's a ring. Okay. Now an ideal, J is prime. Oh, I guess let me call it I because I'm gonna need three ideals. So I is prime if and only if, whenever JK is contained in I, then J is contained in I, or K is contained in I. And I guess really I don't want to distinguish between JK and KJ, so I think it's safe for everything from here on out to be commutative anyway. Yeah, let's say that R is commutative. I mean, there's reasons to study non-commutative rings and stuff, but going forward, we're really looking at commutative rings. Mostly with unity, except that like the ideals are subrings and they don't have unity, so maybe we want to keep that in mind. But anyway, it's sort of a similar thing, right? And let's remind ourselves, right, that A, B, the principal ideals, right, are contained in I, if and only if. How do I want to say this? What I want to say is this. Let me just look at this thing up here, right? So A divides BC if and only if BC. Now I am using commutativity along here. Is an element of A, right? And that's if and only if BC, right, is contained in. Oh, sorry. One more. Let me do one more. If and only if BC is contained in A, right? That's if and only if, BC is contained in A, right? So the ideal A is prime if and only if when this happens. So let's say that the ideal A is prime. So we'd have to have B contained in A or C contained in A, right? But that's equivalent to saying A divides B or A divides C, right? So again, there's an equivalence between kind of division and ideals here, right? Now the generality here is that this I, J, and K don't have to be principal ideals, right? If we're in a principal ideal domain, this is almost completely general. So later on, we talk about those. That's the case, but in general, these don't have to be principal ideals. Okay. Let's see, but nevertheless, it's true. So here's a fact. I think I call it a theorem in the notes. I subset of R. Okay, again, these are always going to be commutative for this lecture. Is prime if and only if whenever. So let's say whenever A B is an I, then A is an I, or B is an I. Right, so we're going to say that's equivalent to being prime. Okay, so there's two directions here, right? So let's call this thing star, right? And let's see that star implies I is prime. Okay, so suppose that J and K are ideals and JK is a subset of I, right? We need to show that J is a subset of I or K is a subset of I, okay? So suppose, I guess this is kind of like cases, right? J is not a subset of I. I mean, the other case is that J is a subset of I, we're done, right? So let's say A be an element of J minus I. Okay, and so notice that this A is fixed, it's something in there, and let B, because there's something in J which is not an I, right? Let B be any element of K. So now this is kind of not fixed, it's anything in K, right? Then we have that, AB, because that is in JK, right, is an element of I. All right, so we have that. Oh, wait, there's one more assumption I want to make. Nope, that's all I want to say. Yeah, I want to say that. And then let's see what I want to do now. Wait. Right, sorry, I had to pause for a second. Really easy, but I just was blinking for a second. Right, so let's just say, so I have A, which is a fixed thing in J minus I, because I'm assuming J is not a subset of I, and I have B, an arbitrary element of K, right? Well, I know that AB is in JK, so it's an I, right? So AB is an I. Now, star tells me that either A, so because of this, either A is an element of I, or B is an element of I, right? But A is not an element of I, right? We chose A to not be an element of I. So B is an element of I for all B and K. So in other words, that is K is a subset of I, right? And that's what we wanted to show. We wanted to show that J was a subset of I or K is a subset of I. So if we assume J is not a subset of I, then K is a subset of I. The other case is that J is a subset of I, and we're done, right? So that's good, right? So star implies I is prime. I is prime implies star, right? So I think this is even easier because, suppose A, B is an element of I, right? Then, okay, A, B is an element of I, right? But then, in fact, this is like what I had above, right? A, B, the product of these two ideals, right? This is the principal ideal generated by A, principal ideal generated by B, is contained in I, right? And therefore, because I is prime, A is contained in I, or B is contained in I. Almost seems like overkill in a way, but that means, in particular, that A is an element of I, or B is an element of I. Right, so we're done. Okay, so we have that if and only if. So there's two ways to check if something's prime. You can check this statement about ideals, right? That statement there, right? Or you can check this somewhat easier sounding statement right there. Now it's still ranging over all A and B, and I, right? Although it's actually ranging over all A and B and R, such that the product AB is an I, right? So it's still, usually requires something to check, right? We'll see that. Okay, suppose we're in a commutative ring with unity, then we have this very important theorem, so I will call this one a theorem. So just to make sure we got this right, R is a commutative ring with unity. I need to call those something like, I don't know, pre-integral domain or something. Then I is prime. And I is an ideal of R. I is prime if and only if R mod I is an integral domain. Oops. Good. All right. So notice by the way that once we have this, we have that 0, the ideal with just 0, right? In an integral domain, the ideal with just 0 is prime. Right? And maybe that's easy enough to prove directly, right? But it follows from that because, R mod, the trivial ideal, right, is just R, right? Or at least it's isomorphic to R. I mean, it's just R. May as well just say it's R, right? Okay, so again, this is an if and only if, so there's two directions, right? So suppose I is prime. Okay, so what do we need to show? We need to show that R mod I has no zero divisors. Okay, so let A plus I and B plus I be in R mod I, right? And let's say that A plus I, B plus I product, right, is equal to 0 plus I, which is just I. So what does that tell me? What is this? This is AB plus I, right? But what this tells me is it tells me that AB is an element of I, right? Because this thing is equal to that thing, okay? But then we know that A is an I or B is an I, right? But that tells me precisely that A plus I equals 0 plus I, or B plus I equals 0 plus I, right? So the only way we can have a product giving us 0 is if one of the things in the product is 0, right? So that's what it means to be an integral domain, right? So that tells me that if I is prime, then R mod I is an integral domain, right? And in the other direction, suppose R mod I is an integral domain, and right, AB is an element of I, right? Then what does that tell me? It tells me that AB plus I equals 0 plus I. So is the 0, right, in the in the quotient structure, right? But on the other hand, this is A plus I, B plus I equals 0 plus I. All right, now we're in an integral domain, so either this is equal to 0 plus I, or this is equal to 0 plus I, right? But what does that mean? It means either A is an I or B is an I, right? Which is what we wanted to show, right? So this says that if I take A, B, and I, then I get A is an I or B is an I, so I is prime. Right, good, that was easy. Okay, maybe, I mean, think through it yourself, right? But that was a pretty direct argument. And maybe it shows you why the prime ideals are what they are, because, that proof works in some sense. Good, okay. Yeah, so I have here the commutative ring with identity is an integral domain if and only if the 0 ideal, right, the principal ideal, which is 0, right, the trivial ideal, is prime. So that's a thing to remember. Okay, so the next thing up is maximal ideals. And so I subset of R is a maximal ideal. Again, I think I'm just pretending everything's commutative with unit here, right? So we're in that sort of situation. If and only if. I haven't actually thought about which of these things are true. I mean, I probably have at some point, but I haven't recently thought about which of these things are true when you're not assuming commutativity or unity, but I also feel like that's just sort of confusing things more than we need to do it right now. So I subset of R is a maximal ideal if and only if there is no in between ideal, right? There is no ideal I prime, which is a proper subset of R, right? So a proper ideal, such that I is strictly contained in I prime is strictly contained in R. Let's see. I guess one thing we don't do in this class is talk about like how to create maximal ideals or the existence of maximal ideals and principal ideals. Maybe partially because that uses the axiom of choice. It's like almost equivalent to part of the axiom of choice. Kind of a deep subject. But it also sort of doesn't come up in anything we're actually doing later. It's kind of like saying every vector space has a basis, even the infinite cases, right? Which we also didn't do in the linear algebra class for the same kind of reason. And in fact, I think probably knowing knowing certain things about the existence of ideals, principal ideals and maximal ideals probably implies the basis theorem too. So they're probably equivalent to each other. This is all sort of set theory type stuff. So notice one thing here is this, that so if, and we'll use it like this. So if I proper ideal is maximal, and remember we're in an ideal with 1, right? Sorry, we're in a ring with a 1, with a unit, right? And A is in R minus I, right? So not in I. So it's something sort of witnessing that this is a proper subset. Then the ideal generated by A and I has to be all of R, right? But we saw earlier that this ideal generated by A and I is just A plus I, and this is just literally the sum of things, right? So this is just things of the form RS plus, RA plus B for B and I, right? So it's literally just the sum of elements, an element from here and an element from there, right? And so particularly what this tells me is it tells me that, this is R, right? So I can get 1, right? So in other words, I can get that RA plus B equals 1, right? For some R and R and some B and I. Okay, so we'll use that in this way. Okay, and you can do lots more with this than we're actually doing in this class. Like if you look at courses on just commutative algebra, they'll do even a lot more stuff with these ideas. Okay, so let's see, what do I want to say? Oh yeah, so and I think maybe we're going to use this in the next thing, right? So there's a theorem that's like the above. I subset of R is maximal if and only if R mod I is a field, right? So there is a difference, right? So dividing out by a prime ideal gets you an integral domain. Dividing out by a maximal ideal gets you a field, right? So let's prove this. Okay, and again, it's an if and only if, so there's 2 directions. So I is maximal. So we're assuming I is maximal. All right, let A plus I not equal to 0, right? So not be I, all right. Then what we know, just as I mentioned above, is that this A plus I must be all of R, right? So in particular, we could get that RA plus I, right? So up here, right, I said that I can get 1, right, is RA plus B, right? So RA plus I is definitely going to give me 1 by taking some elements of I, and then I could just say plus I, right? So we're interested in the properties of R mod I, right? So I'm sort of looking at those things. But what does this tell me? It tells me R plus I and A plus I, when I multiply them together, give me 1 plus I. And well, what does that tell me? That tells me that R plus I is A plus I inverse in R mod I. I mean, One thing that might be fun is taking some of these things or using this notation and thinking back about how it applies to, the number theory stuff we were learning a long time ago, right? Because Zn is just Z, the ring, over, and it's a commutative ring with unity, right? Over in Z, right? This is an ideal, right? And we'll tend to write this in also like this, right? The ideal generated by n, right? Like that. Good. Okay, so we have here that if we have a maximal ideal, then we have a field, and now I want to go the other direction, right? If R mod I is a field, want to show that I is maximal. And the argument's kind of the same in a sense, right? So it's a field, right? So let A be something which is not in I, right? Consider A plus I. This is an element of R mod I, and it's not 0, right? So it has an inverse because I'm assuming R mod I is a field, right? So I have some B plus I times A plus I, right? Which is giving me all of R, right? And so in particular, right, I can get, AB plus something in I, let's call it C, right, is equal to 1, right? So I get that. Yeah, let's see. So I'm going to show it's maximum. But this in turn shows me, right, that A, like AB is definitely in A, right? Because this is A times R for anything in R, plus I, right? This is something in I is going to give me all of R, right? Because this is giving me an ideal generated by these things. It contains 1, right? The ideal generated contains 1, so it's got to be all of R, right? But this is exactly what I needed for maximal, right? I took something, so let's just sort of review that, right? I took something A, which is not an I, and we showed that if we generate the ideal from A union I, then we get all of R, right? So that means there can't be any in-between ideals, right? Otherwise, we'd be able to build one in between, right? So that tells me that I was maximal. The last thing I'm going to show here is that, and we've actually already shown it, is that I is maximal implies I is prime. That's something that'll come up and be useful later. And really, we're just saying, well, I is maximal implies R mod I is a field. That implies R mod I is an integral domain, and that implies I is prime, right? So we're sort of following these implications that way and getting that implication there. And just to point out that we need the something, we need at least the unit, right? So here's an example, sorry, messy. If we have R equals 2Z, okay, this has no unit, right? These are just all the even numbers, okay? But it is a ring, right? And then I claim that I equals 4Z, right? Which if you like would be like 2R, right? Is a maximal ideal. Okay, and that's easy enough to show. I mean, there's not too much room. You just have odd and even numbers there. So you can't make any bigger ideal than that, right? And it's true that that 4 is an I, and 4 equals 2 times 2, right? Which is in R. 2 is in R, but 2 is not an element of I, right? So in this sort of weird case, right, 4Z subset of 2Z is maximal, but not prime, right? So we're really using the unit, along the way there, right? Now this is a commutative ring, right? So this is an example where I'd need to throw away commutativity, but if I just throw away having a unit, right, then that last theorem gets messed up. Anyway, that'll be it for this one.